Volume with known cross-sections. Objectives. By the end of this lesson, you should be able to determine the cross-section of a given three-dimensional object, visualize the three-dimensional object given the base and cross-section, write a formula for the area of the cross-section with respect to x or y, and set up an integral with respect to x or y that will yield the volume of the object using the correct limits of integration. We're going to begin our lesson by defining a cross-section. A cross-section of a solid object S is the plane region formed by intersecting S with a plane. So the next few lessons we're going to take a look at involve volumes of three-dimensional objects. And in previous classes, you've looked at some pretty standard three-dimensional objects that have nice volume formulas, such as a sphere or a cone or rectangular prisms. But our focus is going to be on sort of weirder three-dimensional objects. And to find those volumes, we're first going to need to identify this cross-section notion. So here's an awkward looking three-dimensional object here. So this whole object would be considered S. And we're interested in, sort of informally, a cross-section is a slice of a three-dimensional object. So what we think about doing is we think about intersecting the entire object with a plane. So we should try to think about a plane as a sheet of paper. So imagine slicing this object with the sheet of paper. What would the resulting cross-section, what would a slice look like? So here's this object, and a slice right here from this angle looks like it would take on the form of a square. So right here at this x value, it looks like if we were to slice this three-dimensional object, each of our cross-sections would look like a square. And so we may not always have cross-sections that are nice geometric shapes like squares and circles and such, but for the first couple lessons, that is what we are going to focus on. Okay, so before we go any further, I really want to make sure this idea of a cross-section is understood, and really being able to visualize cross-sections and these three-dimensional objects, because these next few lessons are very visual. So on this first example on the top left, I have this solid object, this three-dimensional object, and one of the things I want you to notice is that it is up against a two-dimensional plane. So here I have an x-axis and a y-axis, but I'm still looking at this three-dimensional object. It sort of looks like a pyramid on its side. And if I were to slice a cross-section, so intersect this three-dimensional object with a plane, it looks like in the previous example I would have a square. And one of the things I want you to observe, if you haven't already sort of thought about it, is there are a few different ways that we could take a cross-section. There are a few different ways that we could slice this three-dimensional object. Namely, the two ways that we would want to focus on is slicing vertically or slicing horizontally. But we have a different name for that. We call slicing vertically perpendicular to the x-axis. So we are going to have these three-dimensional objects sort of on or thinking about it against this xy plane, and we're going to be able to slice vertically, so perpendicular to x, or we're going to slice horizontally, so perpendicular to y. And we'll get a better idea of how to do that as we start to look at the formulas a little more. But right now, it would be best to slice this object vertically, so perpendicular to x, because that's a nice shape. It looks like just a square for us. Moving on to this second image here, I have this three-dimensional object that has this curve look to it, but if I were to slice to find a cross-section of this three-dimensional object, I would see that it is formed by a bunch of triangles. So now we're starting to see different cross-section shapes. Again, they're nice shapes like squares and triangles. So these bottom two images sort of lead into where we're headed, which is we are going to try to create ourselves these three-dimensional objects, knowing what the cross-section's shape is. So going back to the title of the lesson, volume with known cross-sections. So we're going to have some base for the solid, and we're going to stack side by side, really close. So this is a good visual of what we're doing. We're going to stack next to each other a bunch of different cross sections of varying lengths and widths depending on the base. So here, stacking a bunch of squares next to each other creates this three-dimensional object, and we're going to find the volume of that three-dimensional object. And then over here, we're stacking a bunch of triangles together to again form a three-dimensional object, and we're going to be interested in finding the volume of said object. And here are two more examples of the solids we're going to be creating with our different cross sections. So in this example, I have cross sections that are rectangles. And then in this example, I have cross sections that are semicircles with varying diameters depending on that base shape that we're going to take a look at a little bit closer. So before we get into the calculus formulas, there are a couple of geometry formulas specifically for area that you are going to need to know in order to be able to set up these integrals that will allow us to find volume. So these area formulas must be memorized. A circle, so pi r squared, a semicircle, a half pi r squared, a quarter circle, so 1/4 pi r squared, a basic triangle, so 1/2 base times height, but more than that, we'll need to know the area of an equilateral triangle, which is radical 3/4 sides squared, and an isosceles right triangle, so 1/2 sides squared are the triangle formulas we'll need, and then a square, so that's side squared, and a rectangle, which is base times height or length times width. Alright, so we can finally take a look at the calculus formula for finding the volume of an object with known cross sections. And we're going to first start by looking at cross sections that are perpendicular to the x-axis. So we're thinking vertical slices. So we're going to suppose that we have a solid body, a solid three-dimensional object that extends from x equals a to x equals b. Then we're going to let a of x be the area of a vertical cross section at some x value. Then the volume of the solid is given by the integral from x equals a to x equals b of a of x dx. So let's break it down looking at this solid on the left. So here we have this solid body that extends on the x-axis from x equals a to x equals b. And this solid is composed of a bunch of triangles. So those are my cross sections. But each individual triangle has a different area depending on where on the x-axis that particular cross section falls. So what I mean is that this little triangle drawn here corresponds to a particular x value, call it x1. So I can find the area of this particular cross section using a known geometric formula. So maybe this is an equilateral triangle, so we have a known geometric formula for it. So as long as I can find the base right there, then I can find the area of this particular cross section using the square root of 3/4 sides squared, because this length right here would be a side. So once I find that area, then what I need to do is add up every single cross section, every single equilateral triangle as I continue to move from A to B. So at this x2, let's call this one over here x2, I could find the area of this particular cross section. So what I'm doing is I'm adding up every single one of these individual cross sections. And when I think about adding up a bunch of different shapes, I should think about this notion of an integral. So I'm adding up all of the areas from x equals a to x equals b, the areas of my cross sections. The cross section that I have in this left example is a nice geometric shape. It looks like an equilateral triangle. We'll get more specific with further examples. So I would have to use the formula for an equilateral triangle on this example on the left. Taking a look at this example here on the right, so here I have my x-axis, so we would say this extends from x equals a to x equals b. This kind of looks like a weird turkey bone here. And this is one of the cross sections, so here's an a of x example right at some value x on the x-axis. Now this does not have a nice geometric formula for this squiggly looking cross section. But if I were given the area of each cross-section as a function of x, then I could, if I had that a of x formula at every single x, I could find the volume of this particular solid. So sometimes we'll be given the area of the cross-section formula. So let's say I was given a of x, but sometimes I might need to find a of x myself if the cross-section is a nice geometric formula. So here, a of x would involve using, if these are equilateral, radical 3 over 4 sides squared, where we're going to need to write s as a function of x somehow, because this is a of x. But over here, if it is a weird cross-section, I can still find the volume if I know the formula for the cross-section. Alright, so this on the top is just a repeat of the formula that we just took a look at. So if we have a body that extends from x equals a to x equals b, my volume formula, provided I know the cross-section, is the integral from a to b of a of x dx. So in this first example, we want to find the volume of the solid that has cross-section area a of x equals x plus 2 with x values falling between -1 and 3. Alright, so this would be one of the easiest types of problems to set up because we're told the area formula for each individual cross-section as it extends from -1 all the way to 3. So first let's set up the integral and then let's try to visualize a solid. So my volume formula is going to be the integral from x equals -1 to x equals 3. So here's the domain. So I'm going from x equals a to x equals b. And the general formula is we're going to go ahead and stick the area of the cross-section formula into the volume formula. So we're told the area of each individual cross-section at any x value is x plus 2. So my volume formula is now the integral from -1 to 3 of x plus 2 dx. Now, in this section, we've already covered many definite integrals of all forms, so we're not going to focus on the solutions. We're going to obtain the solutions using our graphing calculator. These are all definite integrals. Our graphing calculator can evaluate them. It's all about the setup. So this is the setup required to find the volume of the solid that has cross-section area a of x equals x plus 2. So now let's try to think about what's happening. I'm going to have some solid object that extends from -1 to 3. So I'm going to draw just anything that sort of looks three-dimensional. So I don't know, something like this maybe. And it has some weird cross-sectional shape. So let's say every cross-section has this weird shape, kind of like that turkey leg. So I don't have a formula to find the area of this particular shape, but I'm told that at any x value, so right here at this x value, where this weird looking shape occurred, the area of that cross-section is x plus 2. So let's say this x value right here, x1 equals 1. The area of this cross-section right here is found by applying this formula. So a of 1 is 1 plus 2, so the area of this cross-section is 3. So I'm adding up each of these individual slices from -1 to 3 using this area formula x plus 2. So here's the setup of my integral, and again, at this point we would use our graphing calculator to find the exact area, which turns out to be exactly 12. Okay, so now moving on to examples that we are more likely to see. We have the base of a solid is bounded by y equals x squared and y equals 1. Sketch the region and find the volume of the solid for each of the following cross-sections taken perpendicular to the x-axis. So there's going to be 5 different volume formulas set up here for each of these different cross-section shapes. So first we're going to need to draw the base of the solid, which is bounded by these two functions, y equals x squared and y equals 1. And we have to be extremely accurate in graphing these two functions because we're going to need to find their points of intersection. Those x values are important to setting up our limits of integration. So on this xy plane here, I already know exactly what the limits of integration are going to be. So I'm going to tell you we're going to label 1 to be 4 tick marks away, and then -1 to be 4 tick marks to the left. So instead of each tick mark being 1 unit, they're all going to be 1/4 of a unit. So 1 and -1 are the only values we're going to label. And then same thing for the y-axis. I'm going to label 1, 4 tick marks up, and then we'll go ahead and also mark -1, 4 tick marks down. So we can first graph y equals 1. Y equals 1 is the horizontal line at 1. So here is y equals 1. And then y equals x squared goes through 0, 0. And I can also graph by plotting points. So if I plug in 1, I'm going to get out 1 squared, which is 1. And if I plug in -1, -1 squared is also +1. So if I go ahead and sketch this region of where the two graphs intersect is going to be the base of my solid. So I'll go ahead and just highlight that part in a different color so I know specifically the base region that I'm talking about. So here's the base of my solid. And I have cross sections taken perpendicular to the x-axis. So that means my cross sections are going to be vertical. And the first thing that we're going to do is use cross sections that are equilateral triangles. So let's go ahead and set up part A. So A, the volume, is going to extend from values along the x-axis. And so that's why we needed to be very careful about finding our points of intersection. So the base goes from -1 on the x-axis to +1. So I'm going to set up my integral from -1 to 1. And in general, we have to substitute in the area formula right here. So I'm just going to go ahead and put a of x needs to be input right here in the integrand, where a of x is the area of each cross section. So right here next to equilateral triangles, I'm going to remind you of the equilateral triangle formula. So radical 3/4 side squared. But side, I don't want to just put s right here, especially because there are x's as my variables, my limits of integrations, and the variable of the integrand. I don't just want to go ahead and put s in. So that's not how we use the area formulas. I can't just substitute them in with the variables that I'm used to. So if this were rectangles, I couldn't just put L times W here. I have to make them into functions of x depending on the problem. So I can go ahead and substitute in radical 3/4. And what I need right here is s as a function of x. So I'm going to go ahead and write that intermediate step, at least for now. So what I need is the side length of my equilateral triangle as a function of x. And then I'm going to have that squared, dx. So now what I'm in search of is s of x, the side length of my equilateral triangle. So until we get pretty good at this, I would advise every single time drawing a little sketch of a particular cross section. So since my cross sections go vertically, here would be the base of my equilateral triangle. And it's sort of hard to imagine because, so here's my x-axis, here's my y-axis. This is supposed to be three-dimensional, so what I'm going to do is just draw it. Whoops, I guess that was pretty bad. Something like that. So here is my equilateral triangle, and here is the base, which is also the side length. So this side length here is the s of x that I'm in search of. So the length of this side, so this is just some generic x value, the length of this side is going to be top minus bottom. That's how I find the length of this particular base of this one particular equilateral triangle, but I've generically chosen this equilateral triangle to be at x. So here what I'm going to do is top minus bottom. So I can label my functions here to help me remember that this top function is y equals 1 and this bottom function is y equals x squared. So S of x, the side length of my equilateral triangle, is 1 minus x squared. So that's what I'm going to substitute in right here. So my integral will become the integral from -1 to 1 of radical 3 over 4 of the quantity 1 minus x squared dx. So I needed to substitute in my equilateral triangle formula, but I needed to be careful and find the exact side length of the equilateral triangle at the generic value x, where x could have been any point from -1 to 1. So I could have chosen to draw my little equilateral triangle over here at this generic x. But notice that the length of the side is still top minus bottom, so 1 and then minus the bottom of this is x squared. And we want to be careful too and make sure that our function is in terms of x, so that our entire integral has the same variable throughout. And we'll see why as we get to horizontal cross section. So for now we have x equals -1 to x equals 1, and then our side is in terms of x, so 1 minus x squared dx. So this is the setup of our integral, and again the focus is on the setup. We can solve this on our graphing calculator from here. Alright, so now moving on to setting up part B, where our cross sections are squares. So this should go a little faster now. We have the limits of integration, those stay the same. We have from -1 to 1. And again, what has to go right here is our area formula, A of x, where A of x is the area of the cross section. So remind ourselves up here, the area of a square is side squared, but again, we cannot just put s squared right here. It wouldn't make sense because there are no x's. We need to write s as a function of x. So what we need right here is s of x squared. So what needs to go right here, change colors, what needs to go inside of this is s of x, the side length for each individual square at different places x. So again, I'll just choose the same x value to draw myself a little square. So here my square, I have to try to imagine, for one, that I drew a nice square, but two, that these squares are coming out at me, that they're kind of sticking up and coming at me, because this is the base of my solid. So imagine that I'm staring straight down at my solid right now, and so that I have these squares that are coming straight up at me. So here's my square, and then the side length of my square is once again the same as the side length for my equilateral triangle. So the side of this square here is still top minus bottom. So the top was 1 and the bottom function is x squared. So that's the length of this side here. So that's exactly what I can substitute in to s of x. So here's my general area formula. So side squared, but the side is specific to this particular base, which is found by doing top minus bottom. So 1 minus x squared as a quantity squared dx. So here is the setup for my volume, and again the focus today is the setup. We would solve this using our graphing calculator. Alright, moving on to part C. So now we have cross sections that are rectangles with height 2. So the volume still extends from -1 to 1. And my area formula is again what I need to substitute in as a function of x dx. So to remind ourselves, in general, the area of a rectangle is base times height. But we're told here that the height is always 2. So in other words, my area formula becomes just 2b. So once again, I just cannot substitute 2b in here. My variables don't match. I have x's and b's. So I need to rewrite b, the base of my rectangle, as a function of x. So what needs to go in here is 2, and then I'm going to need to multiply by, what goes in here is b of x. So that's the base of the rectangle as a function of x. So once again, let's choose some generic x value and think about drawing my rectangle of height 2. So what we're imagining here is that here is the base of the rectangle that extends from this top function, which was y equals 1, to this bottom function, y equals x squared. So this right here is b of x. This is the base. And my height, no matter where, I went a little too far there. My height, no matter where I'm at on the x-axis, is always 2. So just to show, I'm going to draw another rectangle. So here's the base. So notice the base is changing as I pick different x values. So let's call this x2 and this one was x1. The base is different depending on every x value. This base is longer, but my height, it's only going to stick out at 2 every single time. So again, if you're trying to think about looking at this straight down, before those squares were growing. So they were little over here and the squares got bigger. So right here at x equals 0, I had the biggest square coming out at me, and then the squares got smaller and smaller as I moved along. Here, the base of my rectangle is getting bigger every time, but the height, it's only coming out at me 2 units every single time. So just to draw one more at this, x3 value, the base stops right there, so top minus bottom, but the height comes out at me only 2 every single time. So again, the base is top minus bottom. So 1 minus x squared yet again. So the setup is really the key to all of this, and it's really to be able to visualize and understand what the solid is going to look like. So here is the answer to part C. This is the setup needed to find the volume of the solid with this base and cross sections that are rectangles of height 2. Alright, moving on to part D, and we'll also look together at part E. And I'm sure you're thinking at this point, if you've kind of got it down, oh, okay, I get it now. But semicircles and quarter circles work a little bit different than the other shapes. And we'll draw the picture and take a look at why. So for part D, my volume formula, so the limits of integration are still -1 to 1. I still have to substitute in a of x. And we'll remind ourselves the area of a semicircle is 1/2 pi times the radius squared. So I'm going to need to substitute in my radius as a function of x. So I can go ahead and plug in 1/2 pi, and then I'm going to need my radius as a function of x squared. So what needs to go in here is my radius. Alright, let's draw a semicircle now. So at some generic x value, I'm going to choose to draw the diameter along the base of my solid. So notice I said the word diameter. This is the diameter of the semicircle. So if I draw my little semicircle, so imagine these are coming out at me again, this whole thing right here is the diameter as a function of x. So I'm going to call that d of x. So we've previously found this length a couple times now, top minus bottom, is 1 minus x squared. But again, that's the diameter. So the relationship between the diameter and the radius is that the radius is half the diameter. So r of x, what needs to go right here, is 1 minus x squared over 2. And now at this point, I'm going to go a little bit further and do some simplifying, because some students end up getting it wrong at this point because of the simplifying aspect to it. So here, this entire quantity, 1 minus x squared over 2, is being squared because it is the radius. So on the outside here, I'm going to go ahead and rewrite this as the integral from -1 to 1 of pi over 2. So I just put the pi on top because this is like pi over 1. And then the top part of this is squared, so this is 1 minus x squared squared. So this squared distributes over division. So over, and then 2 would be squared as well. So there's a 4 there, dx. So what I would do at this point is pi is a constant. The bottom, 2 times 4, is being multiplied. So this is pi over 8, the integral from -1 to 1. And then 1 minus x squared squared dx. So this is the formula that will allow me to find the volume of my object when semicircles are the cross sections. Alright, and so finally we're moving on to quarter circles. So for part E, the volume extends from x equals -1 to x equals 1. And so now the formula for a quarter circle is 1/4 pi times the radius squared, where again we're going to need a radius that is a function of x. So now if we were to draw a quarter circle here, the radius would actually extend along the base of the solid. So if I were to draw a quarter circle, it's going to look something like this. So here's my quarter circle. Whoops. And we can see that this top minus bottom is the radius, not the diameter. So when we have semicircles, the top minus bottom from the base is actually the diameter. But when we have quarter circles, what extends along the base is actually the radius. So if I'm looking for r of x, top minus bottom, is 1 minus x squared. So that's what gets substituted into r, is just 1 minus x squared. There's no need to divide it by 2 because top minus bottom was the radius, whereas here top minus bottom is the diameter. So here is the setup that will allow me to find the volume of my solid where the cross sections are quarter circles. Alright, so now we're going to look at what happens when we're trying to find the volume of an object with known cross sections, but the cross sections are perpendicular to the y-axis this time. So we're going to have horizontal cross sections. So now we need to suppose that a solid body, a three-dimensional object, extends from y equals c to y equals d. We're going to let a sub y now be the area of a horizontal cross section at y. Then the volume of the solid is given by the integral from y equals c to y equals d of a of y dy. So it looks like the exact same formula because the only thing that has changed is the variable y. So now our cross sections, if we take a look at this picture, are horizontal. So each of the slices that we take is going to be perpendicular to the y-axis. So this purple square here is my cross section taken by imagining slicing a sheet of paper through this prism. And each of those cross sections is a square. So at this y value right here, the area of the square is called a of y. So now our limits of integration are from along the y-axis. So this point down here would be from y equals c all the way up to up here. This would be y equals d. So this would be the ending limit of integration, the upper limit of integration, and then c would be the lower limit of integration. So remember, y values, smaller y values are on the bottom, bigger y values are on the top. So we always want to go from the smaller number to the bigger number for limits of integration. And the main thing that changes here is we're going to need our area function to be a function of the variable y instead of the variable x. And we'll see how that affects some of the work we need to do when we solve a problem. So once again, here is that volume formula that now is a function of y as opposed to a function of x because we have horizontal cross sections. And we're going to do that basic type of example where we're asked to find the volume of a solid that has cross section area given by a of y equals pi times 4 minus y squared, with y values coming from 0 to 2, the interval from 0 to 2. So this is that easy type of problem where we're given the area of each cross section. We don't have to find it ourselves. So we're just plugging our information into this volume formula. So volume equals the integral from y equals 0 to y equals 2 of a sub y, or a of y, and a of y was given to us explicitly as pi times 4 minus y squared, and then we add the differential dy. So this is the volume of our solid that extends from y equals 0 to y equals 2. So we don't know exactly what this object looks like, but we know that it goes from y equals 0 to y equals 2. And our cross sections are now taken perpendicular to the y-axis. So there's this pi here, and I imagine maybe this is a radius. So this is definitely some part of a circle, or maybe a circle as the cross section. So let's say, I don't know, these came from semicircles. So we might have this particular semicircle be at the value y as one of the cross sections. So maybe this shape, I don't know, looks something like this. It's a bunch of semicircles of some kind. So this would be our actual three-dimensional object extending from y equals 0 to y equals 2, but now the cross sections are going horizontally. So imagining that the these semicircles or some form of a circle because of this pi here is coming out at me from my xy plane, but this time instead of the regions going vertically up or down, my semicircles coming out like this, they're coming out at me from a different direction. So it's the only difference, and we'll see how the y variable changes some of the setup we have to do for the next type of problem. Alright, so moving on to the next more common type of example, we have the base of a solid is bounded by y equals x cubed, y equals 0, and x equals 1. So I've already gone ahead and drawn these three graphs. So y equals x cubed is this purple curve, y equals 0 is the x-axis, and x equals 1 is the vertical line at 1. So my region is the intersection of all three of these graphs, so it's this little region here that's sort of looks like a triangle, but this portion here is a curve. So it's not exactly a triangle, but it sort of has that general shape. So that's the base of my object. So sketch the region, we've done that, and find the volume of the solid for each of the following cross-sections taken perpendicular to the y-axis. So we're going to have horizontal cross-sections. So we'll just go ahead and write that down as a reminder that we're going to have horizontal cross-sections, and here are each of the cross-sectional shapes. So we're going to have 5 different setups here for the volume of each. So let's go ahead and start with part A, equilateral triangles. Now my volume formula, I am going to make sure to label my limits of integration with the appropriate variable so I don't forget that my integrand also needs to be in terms of that same variable. So on the y-axis, let's go ahead and mark the limits of integration along the y-axis. So the smallest y value here is y equals 0, and my region is going to go up to y equals 1. So this right here, just to sort of shade in my base in a different color, this is my region. So it extends from y equals 0 to y equals 1. So those are my limits of integration. Now on this particular problem, it could be easy to think that the 0 and the 1 are coming from along the x-axis because that is the same interval where this region extends to along the x-axis, but it's not where those numbers are coming from. They are coming from along the y-axis. So for the smallest y value is 0, the biggest y value is 1 of my base. So now in this first example, I'm going to have equilateral triangles that are perpendicular to the y-axis. So the y-axis being the vertical axis, and if I'm perpendicular to it, my little shapes are going to have to be horizontal. So I'm going to have an equilateral triangle. I'm going to draw it trying to look like it's sort of coming out at me. So here's an example of one of my equilateral triangles happening at some y value. So my formula, so in general, what needs to go in the integrand is a of y, the area of each cross-section at different values y. An equilateral triangle area formula is radical 3 over 4 sides squared. But instead of the side length just s, I need s as a function of y now. So this side length here is s of y. And so to represent the length of this side right here, I'm going to have to use right minus left to determine the length of this side as a function of y. So this function here, x equals 1, is already solved for me in terms of y. So in other words, it's an x equals function. I'm going to need to rewrite y equals x cubed so that is in terms of y. So I need to solve it for x. So if I were to solve this equation for x, I need to take the cube root of both sides. So I would get the cube root of y equals x. So now x is a function of y. It's understanding function notation. So now right minus left, the right function right here is x equals 1. So s of y is equal to 1 minus, and now this left side of the function here, that corresponds to x equals the cube root of y. So s of y, this length right here, is right minus left. So I'm going to write that down just to show where it came from. So right minus left is the length of this base to my equilateral triangle. So that is what needs to be substituted in right here for s of y. So 1 minus the cube root of y, dy. So it's very similar to what we do when our cross sections are vertical, but now that our cross sections are horizontal, I need to make sure that all of my functions are in terms of y. In other words, they are solved for x. They are x equals functions that have y's as variables. Or in this case, I have x equals 1, so there is no y variable explicitly because there's just my y to the 0 here. But the main idea is that we are solved for x. So x equals 1 is solved for x, and then y equals x cubed, we've now solved it for x to get x equals the cube root of y. So x is a function of y. So now this is my setup, and at that point I would use my graphing calculator to evaluate this integral. So now let's move on to part B. For part B, the only difference is that our cross sections are squares. So our volume formula is y equals 0 to y equals 1, so still y equals, and I'm just going to be in the habit of always labeling the variable of my limits of integration so that I don't forget to make my integrand a function of y as well. So what goes here is my a of y, and the area of a square is side squared. So what needs to go right here is my s of y. So that's what I'm plugging in and squaring. So the side of my square now, so I'll go ahead and use a different color. So instead of being a equilateral triangle this time, I'm going to have squares coming out at my y value. So my square is coming out, which has a base of s of y again, which is still going to be found using right minus left. So instead of top minus bottom, we use right minus left, and nothing has changed anymore. We already have this in terms of y, so 1 minus the cube root of y is still s of y, and that's what gets substituted in to my area formula for square. So these are the setups required to find the volume of the solid where the cross sections are equilateral triangles and then squares, but they are perpendicular to the y-axis, so horizontal. All right, moving on to part C, we're going to have rectangles of height 2 being the cross sections now. So again, I can think about picking any y value. At that y value, there's going to be a rectangle of height 2 that is perpendicular to the y-axis. So right there, that's going to be the base of my rectangle, and so the height is always a height 2. So we're going to say that that right there is my height 2. My base is b of y. So my base can be found by, again, using right minus left since I'm working horizontally. And right minus left is still 1 minus the cube root of y. So filling in our formula, we have volume extends from y equals 0 to y equals 1. And a rectangle of height 2, well, this formula is base times height, but if the height is always 2, this formula is 2 times the base. So we're going to have 2 times b of y. That's what we're going to need to fill in, dy. So here is my generic area formula for the rectangle of height 2, and b of y is still 1 minus the cube root of y. So we have the integral from 0 to 1 of 2 times 1 minus the cube root of y dy. So this is the setup to find the volume of my 3D object with rectangles of height 2 as the cross section. And now we'll go ahead and do parts D and E together. So for part D, we have our cross sections are semicircles. So we'll have the area extends from y equals 0 to y equals 1. And our area formula for a semicircle is 1/2 pi and then times the radius squared. So 1/2 pi, and in place of r, we're going to need r of y. We're going to need the radius as a function of y squared dy. So this whole thing right here is my area function as a function of y. So let's go ahead and just pick any point, any y value between 0 and 1, so we can draw an example of what the cross section would look like there. So since we're going perpendicular to y, there's going to be the diameter to my semicircle, and we'll go ahead and just draw a little example. So this semicircle is coming out at us, And so this whole thing here is the diameter. So I'm going to call that d of y, which still equals right minus left, 1 minus the cube root of y. But in my formula, I need the radius, so I'm going to have to take half of the diameter. So what goes inside these parentheses is 1 minus the cube root of y squared. So now this is a function of y here, as I need it to be. So this is the integral setup for finding the volume of the 3D object with semicircles as cross sections, which is going to be slightly different than the final part, part E, that has quarter circles as my cross section. So I extend from y equals 0 to y equals 1. And again, just to be clear, I understand that it is kind of tedious to write y equals, but I guarantee that a lot of the mistakes that you're going to make is not changing the integrand to be the right variable. So writing y equals 0 to y equals 1 will help you remember that what cannot absolutely ever go here is x cubed or any x's. So a lot of students are just going to want to say, oh, the left function, oh, that's x cubed, 1 minus x cubed. But writing the differential, writing dy every time, writing y equals every time will help you remember that you can't do that. You have to rewrite the function as a function of y or in terms of y. So finally we're going to have 1/4 pi, and then we're going to have the radius squared. So we need the radius as a function of y, dy. So here is my generic area formula. And now my quarter circles, this is not an example of my quarter circle because now instead of the diameter, we really are going to have the radius be along my region. So I would have something like this. Here's my quarter circle, so that now this is just a radius. So this is r of y. So I don't have to divide by 2 when I'm talking about quarter circles. I can just substitute in 1 minus the cube root of y, right minus left to find r of y. And here's my setup for quarter circles as my cross sections horizontally. Okay, so now to take a look at how I'm going to make sure you really understand this concept, this idea of the cross sections, the idea of the base of each cross section, because again, the next few lessons all have to do with volume and really being able to visualize. You were given a base of a region, and you were given a cross section, and you were given whether those cross sections are to be perpendicular to x or perpendicular to y. So you're going to be creating something that looks like this. So here I have this blown up as big as possible base region. So notice it takes up a good amount of paper on just an 8.5 by 11, but feel free to use thicker cardstock or cardboard so that it's a little bit sturdier to bring with you to class. And so you're going to draw that base and you're going to label it as accurately as possible. And you're going to cut out your shapes of different sizes so that you make sure that they line up correctly with the shape that the base region that you've drawn. So here this region has cross sections that are triangles. So just to look at another example, I have the same base region and my cross sections here are squares. And then to look at another example, I have a different base region and these cross sections are semicircles. But on every single paper there should be, I'm not sure if they're all necessarily done here, these are not from my class, this is from another teacher's class from previous years. What I do want to see is the setup for finding the volume of your particular three-dimensional object. So looks like there's some scratch work down here, but I want to see it done a little more formally. I think the first one did it. So here we go, perfect. So the volume is the integral from 0 to 1, and then here's my area formula. And so here's the setup, and then here's the exact volume of the object that was modeled here in this image. So you should have the base drawn nicely with the axes marked, the x and y axes marked. Your cross sections, you should have a good amount of them so that you can see the difference in the growth of the bases along the region and the setup of the integral.